Good morning, everybody. In the second part of the notes on the dot product, we're going to look at some of the properties of the dot product, focus on how to use it, how we can do arithmetic, what sorts of shortcuts we can use, and what shortcuts we can't. Now, the first thing I want to do is proof of the distributive property, and this is a good example of just working with vectors and how we can build on what we know to prove new facts. Now, because we know the relationship between Cartesian and geometric vectors, we can flip between them and use whichever form is most convenient. So in this case, we're going to prove the distributive property of the dot product using Cartesian vectors. As usual, when we're doing a proof with Cartesian vectors, there's going to be a lot of subscripts, but bear with me. So the first thing we're going to do is write vector u, v, and w in Cartesian form. So u1, comma, u2, that's going to be dotted with, and there should be a bracket there, v1, comma, v2 plus w1, comma, w2. So this is almost by definition. We know how to add vectors in Cartesian form. Once we've got the vectors added, we can do the dot product because we also know how to do the dot product in Cartesian form. Our proof of that did not rely on the distributive property, and so we're not sort of reasoning in circles. Product of the first components plus the product of the second components. So we're going to have u1 times v1 plus w1 plus u2 times v2 plus w2. So we've carried out the dot product, and now we have all scalars. All of those components are scalars, and we know for sure that the distributive property applies to scalars. So let's just expand using the distributive property for scalars. So we're going to have u1 v1 plus u1 w1 plus u2 v2 plus u2 w2. And then we can rearrange. We're going to arrange things so that we can reverse the dot product easily. So u1 v1 plus u2 v2 plus u1 w1 plus u2 w2. And we recognize that those first pair of terms, u1 v1 plus u2 v2, is u dot v. The last pair of terms, u1 w1 plus u2 w2, is vector u dot vector w, and that is equal to the right side. So we have proven the distributive property, and we can use it with confidence anytime we want. So let's work through some examples involving some properties of the dot product. In example 3b, we're asked to simplify vector r plus vector s dotted with vector r minus vector s. Now we could go through and apply the distributive property piece by piece, but we can use FOIL. FOIL is a result of the distributive property. So FOIL works. That means we can carry out the multiplication of the first pair of terms in those binomials. Now we do have to be careful. It's best practice to actually write out what multiplication is being done without doing any simplifications at all. The first pair of terms is, or rather the first pair of factors is r dot r. Now we can simplify that, but we'll do that later on. The outer pair is going to be vector r dotted with negative vector s, and carrying on with the inner terms, we're going to have s dot r, and again, without doing any simplification whatsoever, the last pair of terms is going to be s dotted with negative vector s. So that's using FOIL as a shortcut for applying the distributive property twice. Now we can make some simplifications. R dot r, leave that for now. R dot negative s is the same thing as negative of r dot s, because that negative on vector s is the same thing as multiplying by negative 1, and The associative property for the dot product says that it doesn't matter which multiplication you do first. You can do that scalar multiplication or you can do the vector multiplication. Any order doesn't matter either, so we can bring that negative out front. The commutative property says that s dot r is equal to r dot s, so we can switch the order of those multiplications. And then similarly, associative property gives us negative s dot s. Now you see that there are two terms there that are identical, and so we can just cancel those out. And we're left with r dot r minus s dot s. But r dot r is magnitude of r squared minus magnitude of s squared. That's the simplified version. Notice that this is equivalent to a difference of squares, except we do have to be a little bit more careful when we're writing it. The magnitude is squared, not the vector itself. That's an example of where we have to be a little bit more careful with the dot product. When we're working with the dot product, another thing that we have to be careful with is making sure that we're only trying to dot two vectors. We can't do something like dot a scalar and a vector. So it's possible to write down expressions where this just does not work. So number 5, question 5 on page 376, has some examples of expressions which may or may not work. I'm going to do A, C, and E and leave B, D, and F to you as an exercise. So how do we do this? We apply BEDMAS, and what we're going to do is just write down the kind of result we get. So in part A we've got U dot and then brackets V dot W. V dot W, that's a dot product. It's going to give us a scalar. U is a vector. And we just said that you can't dot a vector and a scalar. So this one does not work because we're trying to dot a vector and a scalar. Over here we have a vector and we're doing a scalar multiplication. V dot W, that is going to be a scalar. We are allowed to multiply a vector and a scalar. That works fine. So that's not a dot product, and we can tell because there's no dot. In part E, if we think about vector v all squared, that's vector v times vector v. We don't really even know what that means. We'll say that one is not possible. There's no multiplication symbol, so it can't be a dot product. It's not a scalar multiplication. We don't know what that means. As I said, B, D, and F, I'm going to let you do as an exercise. All of them work, and I want you to know why they work. So write down whether we're getting a scalar or vector from the multiplications and verify that we're never trying to dot a vector with a scalar or somehow multiply vector times vector. Number 15 on page 377 is another example of where we have to be a little bit more careful with the dot product than we do with regular scalar multiplication of vectors. We're pretty familiar with the fact that when we have two scalars and none of them are 0, then if we have a times b and it's equal to a times c, that means that b is equal to c. We can divide both sides of that equation, ab equals ac, by a, and because a is not equal to 0, then it works. This does not work with the dot product. If we have a dot b equals a dot c, it is not necessarily true that b equals c. Obviously, if b is equal to c, then the equation is true, but that equation being true does not guarantee that b vector equals c vector. So we can show this with a counterexample. Let's just choose, and this is sort of chosen randomly, a vector is equal to 2, 4, and b vector is equal to 2, 0. So let's figure out what a dot b is first of all. A dot b, and I will substitute in, so 2, 4 dotted with 2, 0. A little bit of mental math tells us that's equal to 4. Now let's find a vector c such that a dot c is equal to 4. We don't know what vector c is, but we can try and find its components. And if we can find its components, then we found a c. So a dot c, that's equal to 2, 4. We're going to dot it with the components of vector c, which we don't know. Carry out that expansion, 2 times C1 plus 4 times C2. That's got to equal 4. Now here we have an equation with two variables, C1 and C2, but it's just one equation. This equation has an infinite number of solutions. So an infinite number of solutions. We can choose a solution. Probably the simplest solution to that equation is to say, let's say C1 is equal to 0 and C2 is equal to 1. And then that means that vector C is equal to 0, 1, which is definitely not the same thing as vector B. So even though vector A dot vector C is equal to vector A dot vector B, that does not mean that C and B are the same thing. So this has some unfortunate consequences for simplification. When we're working with a scalar equation at work to divide both sides by the same scalar, there's no operation like that with vectors. You can't undo a dot product by something like division. And that means we can't simplify equations by dividing out common factors if those common factors are vectors, which is a little bit unfortunate, but it just means that we have to do a bit more expansion and we get to do more cancellation, and that's always fun. I have some practice questions chosen for you. I'm going to ask you to also hand in a question just to make sure that you know what you're doing with the dot product and how we interpret it, and I'll let you get to those.